What's up, everybody? It's Chris Shabbat, and I'm back with another Chem 1B video. Today, we're going to go over the rate law equation. So, before we actually get into the example for today, we're going to go over one giant note. So, basically, how do we identify what order we have with respect to certain reactants in a reaction? So, if the rate of change for the reactant X doesn't change the overall rate of reaction, we say that it's zero order. So what we mean by that is it doesn't actually change or impact the rate of reaction for the whole chemical equation. So when the concentration of X doubles from 0.2 to 0.4, the overall rate would remain at 3.0. That goes to say that if you were to triple it, 0.2 to 0.6, the rate would remain 3.0. If you did 0.2 to 1.5 or times any, multiplicity, you would still be 3.0. Now, when the rate of change for some reactant X changes at the same rate as the overall rate of reaction, then we have something that we consider first order. So when the concentration of X doubles from 0.2 to 0.4, the overall rate doubles from 3 to 6. When the concentration of X is 7 times, again, most commonly you'll find either doubled or tripled, but just to show you that it works in extreme conditions as well, I did 7 times, so we could have 0.2 to 1.4. The overall rate is 7 times as well. So it'd go from 3 to 21. And obviously, 0.2 times 7 is 1.4, and 3 times 7 is 21. So the last order that we have to really study in this class is the rate of change for the overall rate of reaction when it's higher, when it's to a higher degree than the rate of change for a reactant. So if this is the case, then we have a second order with respect to that reactant. So what I mean by that is when the concentration of X doubles from 0.2 to 0.4, the overall rate would quadruple from 3 to 12. And when the concentration of X is 7 times, so from 0.2 to 1.4, the overall rate, you don't really have to memorize the exact rules, but if it's anything higher than 7 times, like for example, from 3 to 42, then you know it's second order by process of elimination. If there's no change, or if there is a change, then you know it's not zero order. And if it's above first order rate, then you know it has to be second order by process of elimination. So let's actually try this in practice. So let's go to our example. So today's example problem, the experimental observations in the following table were obtained for the reaction 2A plus 2B plus 2C goes to 3X. And it gives you these 4 experiments that were conducted, right? And it says, what is the order of the reaction with respect to each of the reactants? Write an expression for the rate equation, calculate a value for the rate constant, and calculate the rate of production of X when concentration of A, B, and C are all 0.4 moles per liter. So we're going to go through these one at a time. So let's go to A first. Okay. So how do we even start this? Well, I'd like to use an analogy, right? So let's say you are in a botany lab and you're trying to see how much the sun impacts the growth of a plant, how much the water or the watering tendencies affect the growth of the plant, and the size of the seed affects the growth of the plant. So let's say that you wanted to test the sun. You can't make each of the variables in your pots of plants change each time, right? So like if we're going to test the sunlight, then we should have 3 plants, all of which have the same seed size, all of which have the same watering patterns, and each of which we only change the sun, right? So one would have 1 hour of sunlight a day. The other one would have 2 hours, and the other one would be in sun all day. So what I'm trying to get at is when we're going about these problems, look for the 2 experiments where only one variable is changed. So if we're to look here, let's again just do A first. So we'll do A. Let's first find which experiments we want to use. So we want to find where A changes, but the other ones are the same. So if we look at this one right here, experiment 1 and experiment 2, it actually shows that these are equivalent. These are equivalent, but this changes A, which is exactly what we're looking for. So we just have to ask ourselves at what's happening when A changes and the rate changes. So it looks like A is tripled. So when A is times 3, what happens to the rate? Rate goes from 3 to 9. So that also triples. And if they both change at the same rate, then we know it's first order. Again, this is from the last slide. Now let's try out B. Again, let's find 2 experiments that work out. So let's erase this. Cool. So if we actually look at experiment 1 and 3, A is the same, it's 0.273 in both cases. C is the same, it's 0.4 in both cases. However, it looks like B doubles. So B, when it's multiplied by 2, let's look at what happens to the rate. The rate will go from 3 to 12, so that's times 4. So because this isn't times 0, right, it did change. We know it's not 0 order. And because it's not rate times 2, that means it's not first order. So that means we're left with a second order with respect to B. And then let's go over C. For C, let's find the 2 that we're looking for. So for C, we're actually going to use experiments 1 and 4. In this case, A is the same, B is the same, but C changes. So C doubles. It's C times 2. And then let's look at what happens to the rate. When the C changes times 2, the rate also changes times 2. And because they change by the same amount, we know that it's first order. Cool. So now that we have that, let's go on to part B. So it says write an expression for the rate equation. So now we have to write an expression, and our expressions hold this form. It's rate equals a rate constant K times each of our reactants to the power of which order they are. So again, we have concentration of A, and we said A was first order, so it's to the first power. We have B, and we said B was second order, so it's to the second power. And we said we have C, which was first order, so we have it to the first power again. And this would be all we're looking for this problem. Okay, now on to C. It says calculate a value for the rate constant. So now we're going to look for a value of K. So again, our equation is rate equals K times A times B squared times C. Now, what can we plug in for everything? Basically, we could plug in any row we want as long as we use all the numbers from that row. So I'm going to use the first row, well, simply because it's only the first row, but if you feel inclined to use the second, third, or fourth row, you will get the same exact answer. So again, we'll have R is what? 3. So we'll have 3 equals K times the concentration of A, which is 0.273, times B squared, which is 0.763 squared, also times C, which is 0.400. So if we break this all down, we'll have 3 equals, again, some calculator work, you'll have 0.0636 K. And then again, divide both sides by 0.0636, and you'll get that K is roughly 47.19. Now, typically your K is not that large. For the sake of simplicity, I did take the rates and make them much larger just for this example. So again, learn about what we're doing rather than what the numbers should look like just for this example. This is an extremely large K value. Okay, so now that we have K, it says calculate the rate of production of X when the concentration of A, B, and C are all 0.4 moles per liter. So the way we go about doing this is, again, start just by writing out that we have R equals K, but now we have K, right? So we can put 47.19. And then again, we're going to do concentration of A, concentration of B squared, concentration of C. Okay, now we want to know what R is if we put 0.4 in for this, this, and this. So let's just plug that in. We have the rate will equal 47.19 times 0.4 times 0.4 squared times 0.4. So that's 0.4 to the fourth power times 47.19. And if you were to plug that into your calculator, you'd get a rate of roughly 1.208. And that's your rate. So these are pretty much very typical questions that'll be asked of you when you're given this table over here. And if you have any questions on how to go about either of these or the integrated rate laws, feel free to drop into SI office hours or comment down below. Thank you.